Hello and welcome. I am so glad you are here. Take a moment right now, just a moment, to let everything settle. Feel the surface beneath you, firm and steady and supportive. Feel the warmth around you. Feel your breathing, slow and natural and easy. Whatever the day brought, it is finished now. You made it through. And this time, this quiet time, belongs entirely to you. Tonight we are going somewhere close, relatively close at least, by the standards of the solar system. We are staying inside the inner planets, the rocky worlds that orbit near the sun. But the world we are visiting tonight is in many ways the most extreme, the most dramatic, the most physically hostile of all the planets we have explored. A world that looks, from a distance, like it might be Earth's twin, and a world that up close is about as far from Earth as it is possible to imagine. Tonight we explore Venus, its atmosphere, its surface, its history, and the extraordinary mission that finally revealed what lies beneath its impenetrable clouds. Everything I am going to tell you is true. Every measurement, every discovery, every detail. This is the real Venus, revealed by real spacecraft over decades of exploration, and by the time we are finished, you will understand this strange and beautiful and terrible world in a way that most people never do. Before we begin, take a long, slow breath in. Fill your lungs gently, all the way. Hold it for just a moment, and breathe out slowly, feeling your body soften and release. Let your eyes stay closed. Let the sounds of your environment fade into the background. You are safe. You are warm. And we are about to visit the most extreme atmosphere in the solar system. Let us begin with how Venus appears to us from Earth, because how we see it is very different from what it actually is. Venus is the brightest natural object in the night sky after the moon. On a clear night, it can be brilliant enough to cast a faint shadow. It outshines every star, it outshines every planet. When it is visible, it is impossible to miss, a piercing point of white light either in the western sky just after sunset or in the eastern sky just before sunrise. This is why Venus has been called the evening star and the morning star for thousands of years. Ancient civilizations around the world watched it with fascination and gave it names associated with beauty and brightness. The ancient Greeks called it Phosphorus when it appeared in the morning, and Hesperus when it appeared in the evening, before they understood it was the same object. The Romans named it Venus, after their goddess of love and beauty. In many cultures, this bright wandering light was associated with the feminine, with fertility, with the cyclical nature of time. The Mayans tracked Venus with extraordinary precision, calculating its orbital period to within seconds of the modern measurement. The Babylonians recorded Venus's appearances and disappearances over centuries, building up tables that allowed them to predict where it would be in the sky years in advance. The planet's brilliance made it one of the most carefully observed objects in the ancient sky. Venus appears so bright for a specific physical reason. Its surface is completely hidden beneath a thick, unbroken layer of clouds, and those clouds are made of droplets of sulfuric acid. These sulfuric acid clouds reflect about 70% of all the sunlight that falls on them. For comparison, Earth's clouds reflect about 30% of incoming sunlight. Venus's clouds are among the most reflective natural surfaces in the solar system. All that reflected sunlight is what makes Venus blaze so brilliantly in our sky. The brightness that attracted the attention of every ancient civilization on Earth is the reflected glare of a toxic acid cloud that completely enshrouds an infernal world. Beneath those clouds lies one of the most hostile environments in the solar system. Venus is the second planet from the Sun, orbiting at an average distance of about 108 million kilometers compared to Earth's 150 million kilometers. In terms of size, Venus is almost Earth's twin. Its diameter is 12,104 kilometers compared to Earth's 12,742 kilometers. Its mass is 81% of Earth's mass. Its surface gravity is 90% of Earth's surface gravity. If you stood on Venus, you would feel almost exactly the same gravitational pull as you feel on Earth. In terms of size and mass, Venus and Earth are more similar to each other than any other pair of planets in the solar system, but the similarity ends there. Everything else about Venus is different, drastically, almost incomprehensibly different. The atmosphere of Venus is composed of about 96.5% carbon dioxide, with most of the remainder being nitrogen and trace amounts of other gases, including sulfur dioxide, water vapor, and carbon monoxide. There is almost no oxygen. The atmospheric pressure at the surface of Venus is about 92 times the atmospheric pressure at Earth's surface. 92 times. To experience that pressure on Earth, you would need to descend about 900 meters below the surface of the ocean. It is the pressure of the deep sea pressing on every square centimeter of any object on the Venusian surface. The early Soviet spacecraft that landed on Venus were built like submarines, with thick metal shells designed to withstand crushing pressure. Even so, they survived on the surface for only between 23 minutes and about 2 hours before the combined pressure, heat, and corrosive chemistry destroyed them. The surface temperature on Venus is about 465 degrees Celsius on average. This is hotter than the surface of Mercury, despite Mercury being more than twice as close to the Sun. Mercury has no atmosphere to trap heat, so its surface temperature varies enormously, from about 430 degrees Celsius on the sunlit side to minus 180 degrees Celsius on the dark side. Venus has a thick atmosphere that traps heat so effectively that the temperature is nearly the same everywhere on the planet, day or night, equator or pole. The surface of Venus is uniformly, relentlessly hot, hot enough to melt lead, hot enough to melt tin, hot enough that any spacecraft landing there faces not just crushing pressure, but temperatures that would incinerate unprotected electronics within minutes. What keeps Venus so hot? Carbon dioxide. The greenhouse effect taken to an extreme. Carbon dioxide is a greenhouse gas. It allows visible light from the sun to pass through and reach the surface, where it is absorbed and converted to heat. But when the surface radiates that heat back upward as infrared radiation, the carbon dioxide absorbs the infrared and prevents it from escaping to space. The heat is trapped. The atmosphere acts like a blanket, keeping the surface warm. On Earth, the greenhouse effect raises our average surface temperature from what would otherwise be about minus 18 degrees Celsius to the current global average of about 15 degrees Celsius. This greenhouse effect is what makes Earth habitable. Without it, our oceans would be frozen solid. Venus has taken this process to a catastrophic extreme. The atmosphere contains so much carbon dioxide that the greenhouse effect raises the surface temperature by about 500 degrees Celsius above what it would be without an atmosphere. This is called a runaway greenhouse effect. At some point in Venus's history, conditions changed in a way that drove a positive feedback cycle. As the planet warmed, more water evaporated. Water vapor is also a greenhouse gas. As more water vapor entered the atmosphere, it trapped more heat. The increased heat caused more evaporation, and so on, cycling upward until the oceans boiled away entirely and the surface reached its current extreme temperature. The carbon dioxide from volcanic outgassing no longer dissolved and trapped in oceans and carbonate rocks as it is on Earth, accumulated in the atmosphere and drove the temperature even higher. The runaway greenhouse effect on Venus is one of the most important cautionary tales in planetary science. It demonstrates what can happen when the carbon dioxide content of a planetary atmosphere gets too high and the feedback loops that stabilize a climate breakdown. Scientists study Venus's climate in part because understanding how it went wrong helps us understand how to prevent similar processes from occurring on Earth. Let your breathing slow a little more. You are drifting beautifully. The atmosphere of Venus presses down on its surface from above, dense and hot, and full of carbon dioxide. And above the surface, rising through the lower atmosphere, the clouds. The cloud system of Venus is one of the most complex and visually spectacular in the solar system, though you would need to be above it to appreciate its visual drama. The clouds of Venus form a continuous planet-encircling layer from about 45 to 70 kilometers altitude above the surface. Below 45 kilometers, the atmosphere is too warm for the cloud droplets to remain liquid, and the sky is clear, though thick with haze. Above 70 kilometers, the cloud material thins into a high-altitude haze. Within the main cloud layer, there are distinct sublayers with different compositions and particle sizes. The uppermost cloud deck consists of tiny droplets of concentrated sulfuric acid, formed when sulfur dioxide from volcanic activity reacts with water vapor and sunlight in the upper atmosphere. These droplets are highly reflective, which is what gives Venus its brilliance. The middle cloud layer has larger sulfuric acid droplets mixed with other particles. The lower cloud layer contains still larger particles, possibly including solid crystals of unknown composition. The clouds are not static. They are in constant, rapid motion, driven by the extraordinary winds of Venus's upper atmosphere. At the cloud tops, about 70 kilometers above the surface, winds blow at speeds of about 360 kilometers per hour, flowing continuously from east to west around the planet. These winds complete a full circuit of the planet in only about 4 Earth days, but Venus itself rotates extremely slowly, taking 243 Earth days to complete one full rotation. This means the cloud tops are moving around the planet about 60 times faster than the planet's surface below them. This phenomenon is called atmospheric superrotation, and it is one of the most dramatic examples of planetary atmospheric dynamics in the solar system. Below the cloud tops, the wind speed decreases with depth. At the surface, winds are very gentle by the standards of the upper atmosphere, typically only a few kilometers per hour. But even a gentle breeze in the dense Venusian atmosphere carries a tremendous amount of energy, because the atmospheric density at the surface is roughly 50 times the density of Earth's atmosphere at sea level. A slow, gentle wind in this dense atmosphere would push against any object with the force of a fast-moving current of water. Lightning has been detected on Venus. The evidence comes from radio wave emissions that have the characteristics of electrical discharges detected by spacecraft flying past or orbiting Venus. The source of the lightning is thought to be the clouds of sulfuric acid in the middle cloud layers, where the conditions for charge separation and electrical discharge may exist. Lightning on Venus is a subject of ongoing research, and the details of how it forms in such unusual atmospheric chemistry are still being studied. The cloud system, with its rapid circulation and its complex chemistry, makes Venus one of the most active weather systems in the solar system, despite the fact that there is no liquid water anywhere in the atmosphere or on the surface. The sulfuric acid droplets evaporate and reform continuously. The winds reshape the cloud patterns in ways that are visible from space as dark and light banding in ultraviolet images. Vortex structures form at the poles, large rotating atmospheric features that swirl around the polar regions. Venus is meteorologically alive, even if it is geologically and chemically hostile. Now let us talk about the exploration of Venus, about the spacecraft that attempted to pierce the clouds and reach the surface, and what they found. The Soviet Union had an extraordinary program of Venus exploration, perhaps the most ambitious and successful planetary exploration program of any nation for a specific target. Between 1970 and 1982, the Soviet Venera program sent a series of increasingly sophisticated landers to the surface of Venus. Each one faced the same brutal challenge: to survive long enough in the crushing, burning, corrosive atmosphere to return data before being destroyed. Venera 7 was the first spacecraft to successfully land on Venus and transmit data from the surface in December 1970. It survived for 23 minutes after landing, transmitting temperature and pressure data before falling silent. Venera 8, landing in 1972, survived for 50 minutes. Each successive mission improved on the design, making the spacecraft more robust against the pressure and heat. Venera 9 and 10, landing in October 1975, were the first to return images from the Venusian surface. These images were in black and white and showed rocky, angular boulders on the surface, illuminated by the diffuse orange light that penetrates through the thick atmosphere from above. The landscape looked like a rocky desert, with flat slabs of rock and debris scattered across the surface. It was the first direct visual confirmation of what Venus's surface looked like. Venera 13 and 14, landing in March 1982, transmitted color images from the surface. These are among the most remarkable photographs in the history of space exploration. The images show a landscape bathed in a yellowish-orange light, the result of sunlight filtered through 70 kilometers of thick cloud and haze. The sky, where visible above the horizon, has the color of an orange-yellow smog. The ground is covered in flat slabs of dark rock, interspersed with fine soil. The rocks have a layered, almost sedimentary appearance, suggesting they may have been produced by repeated volcanic eruptions and burial. The surface looks geologically young, with few of the rounded, weathered features you might expect after billions of years of chemical attack. Venera 13 survived for 127 minutes on the surface. Venera 14 survived for 57 minutes. Both were eventually destroyed by the heat and pressure. These images gave us our only direct views of the Venusian surface from ground level. They show a world that is orange and alien and still, bathed in a dim light that filters through layers of cloud and haze, a world where the sky is the color of a deep bruise and the rocks look fresh and sharp despite billions of years of exposure to one of the most corrosive atmospheres in the solar system. There is no wind visible in the surface images, no movement, no sign of change, just rocks and sky and silence. Let your breathing slow even more. You are very comfortable. The atmosphere of Venus presses down on you only in the imagination, while your own comfortable world holds you safe and warm. Let the story drift over you like a gentle tide. But the Soviet landers, as remarkable as they were, could only tell us about the surface and the specific places where they landed. They could not map the planet. They could not reveal the global geography, the large-scale features, the continents and mountains and plains of a world hidden beneath clouds that no optical telescope could penetrate. For that, a different approach was needed. Radar, radio waves can penetrate the thick clouds of Venus. A spacecraft carrying a powerful radar could send pulses of radio waves downward through the clouds, bounce them off the surface, receive the reflected signals, and build up a detailed map of the surface topography. The technique is called synthetic aperture radar, and it had been developed and refined for mapping Earth from space. Applied to Venus, it could do what no camera could, see through the clouds and reveal the surface. The Magellan spacecraft was built to do exactly this. Magellan was a NASA mission launched on May 4th, 1989 from the Space Shuttle Atlantis. It was the first interplanetary spacecraft to be launched from a space shuttle. After a 15-month journey, it arrived at Venus on August 10, 1990, and entered orbit around the planet. Magellan's primary instrument was a synthetic aperture radar system designed to map the Venusian surface with a resolution of about 100 to 300 meters. This was far better than any previous radar mapping of Venus. Previous missions, including the Pioneer Venus Orbiter and several Soviet orbiters, had produced rough global maps of Venus's topography. But Magellan would produce something unprecedented, a nearly complete, high-resolution map of the surface of another planet. The spacecraft entered a highly elliptical orbit around Venus, swooping close to the surface at periapsis and swinging far out into space at apoapsis. During each close pass, as it moved over the surface at high speed, it transmitted radar pulses downward and recorded the reflected signals. By carefully analyzing the timing and intensity of the reflected pulses, the onboard computer and the scientists on Earth could reconstruct the precise shape and roughness of the surface below. Over the course of its primary mission and extended missions, which ran from 1990 to 1994, Magellan mapped about 98% of Venus's surface. This was the most comprehensive mapping of any planet other than Earth ever achieved at that time. When the full dataset was compiled and processed, what emerged was a portrait of a world of extraordinary geological character, a world shaped by forces and processes that were both familiar and deeply alien. Let us now descend through the clouds in our imagination and walk across the surface of Venus as Magellan revealed it. The first thing to understand about Venus's surface is that it is dominated by volcanic features. Venus is a volcanic world. About 85% of its surface is covered by volcanic plains, vast flat regions of solidified lava that have been flooded and reflooded by volcanic eruptions over millions and billions of years. The plains are punctuated by volcanic constructs of every size and shape, from small shield volcanoes barely a kilometer across to enormous volcanic complexes hundreds of kilometers in extent. Venus has more volcanoes than any other planet in the solar system. Some estimates suggest there may be more than 1 million individual volcanic features on the planet's surface. The largest volcanic feature on Venus is a shield volcano called Mat Mons. It rises about 8 kilometers above the surrounding plains and has a base diameter of about 400 kilometers. In shape, it is similar to the Great Shield volcanoes of Hawaii, with a broad, gently sloping profile and a summit caldera. Mat Mons is surrounded by extensive lava flows that have spread across the surrounding plains, overlapping and interlayering in patterns that suggest multiple eruption episodes over a long period of geological time. The question of whether Venus is currently volcanically active has been one of the most important and contested in planetary science. For years, the evidence was ambiguous. Magellan's radar images showed volcanic features that appeared geologically young, with minimal erosion and few impact craters overprinting them. The atmosphere contains sulfur dioxide, which is consistent with ongoing volcanic outgassing, but none of this conclusively proved active volcanism. In 2023, scientists analyzing archival Magellan radar data from the early 1990s made a significant discovery. They found that a volcanic vent near a feature called Mat Mons had changed shape between 2 radar imaging passes made 8 months apart. The vent, which appeared roughly circular in the first image, appeared larger and irregular in the second image, consistent with the collapse and widening that occurs when a volcanic vent erupts and emits lava. This was the first direct observational evidence of ongoing volcanic activity on Venus. Venus is not geologically dead. It is still erupting. This discovery transformed how scientists think about Venus. A geologically active Venus means the planet is still releasing heat from its interior through volcanic eruptions. It means the atmosphere is being continuously supplied with sulfur dioxide and other volcanic gases. It means the surface is young in many regions, actively being reshaped by volcanism. And it means Venus's interior is still hot and dynamic, even if the mechanism of heat release is very different from Earth's plate tectonic system. Earth releases its internal heat through a combination of plate tectonics, which continuously recycles the crust, and volcanism at specific locations. Venus appears to lack active plate tectonics in the Earth sense. There are no clear spreading centers, no subduction zones, no evidence of 2 plates meeting and one diving beneath the other. Instead, Venus appears to release its internal heat through episodic, intense bursts of volcanism that resurface large portions of the planet at once. Some scientists hypothesize that Venus undergoes periodic global resurfacing events, where the built-up internal heat is released catastrophically through an enormous outbreak of volcanism that covers much of the planet in fresh lava before the surface cools and begins to build up heat again. If this hypothesis is correct, the current surface of Venus may be geologically young, perhaps only 300 to 800 million years old, produced in the most recent such resurfacing event. Magellan revealed several geological features on Venus that are unique, found nowhere else in the solar system, or found only in modified forms. One of the most intriguing are the coronae. Coronae are large, roughly circular to oval structures found across the Venusian surface. They range from about 60 to 2,600 kilometers in diameter. They appear as raised rings or rims surrounding a central region that may be elevated, depressed, or complex in topography. They are thought to form when plumes of hot material from the mantle beneath the crust rise upward, push the crust up from below, and then, as the plume weakens or the crust fractures, cause the center to collapse or flood with lava. Coronae are volcanic in origin, but they are different from the straightforward shield volcanoes that build up layer by layer from repeated lava flows. They are the result of a more complex interaction between the mantle below and the crust above. Venus has more than 500 confirmed coronae, and they come in a range of sizes and stages of development that tell scientists about the evolution of these features over time. Another unique Venusian feature is the arachnoid, so named because it resembles a spider web. Arachnoids are volcanic calderas surrounded by a complex network of fractures radiating outward from the central structure, intersected by circular or concentric fractures that together create the web-like pattern that gives them their name. They may be related to coronae in origin, forming through similar mantle-plume interactions, but their specific pattern suggests a slightly different sequence of events. Venus has dozens of confirmed arachnoids. Pancake domes are another feature found abundantly on Venus, but rare elsewhere. These are circular, flat-topped volcanic constructs with steep sides and a distinctive disc shape, looking from above exactly like a stack of pancakes. They form when very thick, viscous lava erupts slowly from a central vent and does not flow far before solidifying. The result is a dome of steeply sided lava with a flat or slightly rounded top. Individual pancake domes can be tens of kilometers across and a kilometer or more tall. They are found scattered across Venus's volcanic plains and highland regions, often in groups. Now let us visit the highest points on Venus, the mountains and highland regions that rise above the volcanic plains. Venus has two large highland regions, somewhat analogous to the continents of Earth, called Ishtar Terra in the north and Aphrodite Terra near the equator. Ishtar Terra is the smaller of the two, about the size of Australia, but it contains the highest peaks on Venus. It is a high plateau with mountain ranges around its edges, somewhat resembling the Tibetan Plateau on Earth in its general character, though not in its origin. At the eastern edge of Ishtar Terra stands the Maxwell Montes, the highest mountain range on Venus. The highest peak in Maxwell Montes reaches about 11 kilometers above the mean surface level of Venus, which is Venus's equivalent of sea level. This makes Maxwell Montes the tallest mountains on Venus and significantly taller than Mount Everest on Earth. The mountains are surrounded by peculiar radar-bright regions that Magellan detected as highly reflective surfaces. Scientists believe this high reflectivity may be caused by metallite compounds that condense out of the hot Venusian atmosphere at the cooler temperatures found at the highest altitudes. at the extreme temperatures near Venus's surface. Certain minerals are vaporized and remain in the atmosphere, but at the slightly lower temperatures of the highest mountain peaks, these minerals condense back into solid form and coat the mountain surfaces with a metallic frost. This metallic frost, possibly made of compounds of lead or bismuth or other heavy metals, makes the highest peaks of Maxwell Montes among the most unusual surfaces in the solar system. Mountains coated in metal, rising above volcanic plains in the dim orange light of a sulfuric acid sky. Aphrodite Terra is larger than Ishtar Terra, roughly the size of South America. It stretches along the equatorial region of Venus and contains several large highland massifs, deep rift valleys, and complex volcanic terrains. The rift valleys of Aphrodite Terra are similar in some ways to Earth's rift valleys, formed when the crust is pulled apart by tectonic forces. But on Venus, where plate tectonics in the full Earth sense does not appear to operate. These rifts may have formed through different mechanisms, possibly related to the mantle plume activity that drives the coronae and arachnoid formations. The Tessera terrain is perhaps the most geologically complex terrain on Venus. Tessera, from the Greek word for tiles, are regions of extremely deformed, highly textured surface material that appear in Magellan radar images as bright, chaotic landscapes of intersecting ridges and valleys running in multiple directions. They look like crumpled foil pressed flat, with structures at many scales overlapping and cutting across each other. Tessera terrain is thought to be among the oldest terrain on Venus, rocks that have been deformed and redeformed by multiple episodes of tectonic and volcanic stress over long geological time. The tesserae may represent ancient crust that has somehow survived the resurfacing events that covered most of Venus and younger volcanic plains. Studying tessera terrain may give scientists their best window into the deep geological history of Venus. Let your breathing settle even more deeply now. You are drifting beautifully. The orange world of Venus turns slowly in your imagination, its thick clouds swirling, its surface invisible to optical instruments, but revealed by the patient radar pulses of Magellan, bouncing back from mountains and plains and volcanoes and coronae, building up a portrait of a world that hides its face behind acid clouds. Venus has an extremely unusual rotation. It rotates very slowly, taking 243 Earth days to complete one full rotation on its axis, but more unusually, it rotates in the opposite direction to most planets. If you could look down at the solar system from above the North Pole, you would see almost every planet spinning counterclockwise. Venus spins clockwise. This retrograde rotation means that on Venus, the sun rises in the west and sets in the east. From the surface of Venus, if you could somehow survive long enough to watch the sky, you would see the sun moving from west to east across the sky. Because Venus rotates so slowly, and because it orbits relatively quickly, a Venusian day, measured from one sunrise to the next sunrise, is actually shorter than Venus's rotation period. One Venusian day is about 117 Earth days, while the rotation period is 243 Earth days. This strange relationship between the rotation period and the orbital period means that Venus's year, the time it takes to orbit the sun, is actually shorter than its day. Venus's year is about 225 Earth days, while its day is about 243 Earth days. It takes Venus longer to spin once on its axis than it takes to complete one orbit around the Sun. You could arrive at Venus, orbit it once, and leave again before it had time to rotate fully underneath you. The origin of this unusual retrograde rotation is not fully understood. One possibility is that a very large impact early in the solar system's history struck Venus at just the right angle to reverse its rotation. Another possibility is that the gravitational interactions between Venus's thick atmosphere and the solid planet below have over billions of years gradually slowed and then reversed the original rotation. The atmosphere of Venus, with its powerful super-rotating winds and the tidal forces exerted on it by the Sun's gravity, may be able to exert enough torque on the solid planet beneath it to modify the rotation over geological time. This is an area of active research. Now let us consider the most profound question about Venus. Was it always this way? The answer, most scientists now believe, is no. Venus may have been very different in its distant past. There are several lines of evidence that suggest Venus once had liquid water on its surface, perhaps even oceans. The abundance of deuterium, a heavy form of hydrogen, in Venus's atmosphere is much higher than in Earth's atmosphere. When water is lost from a planet through a process where the hydrogen is stripped away by ultraviolet radiation and escapes into space, the heavier deuterium is lost more slowly than ordinary hydrogen. The high ratio of deuterium to ordinary hydrogen in Venus's atmosphere is consistent with the evaporation and loss of a large amount of water over billions of years. The more water that was lost, the higher the ratio would be expected to be. The current ratio suggests Venus may have lost an amount of water equivalent to a global ocean tens of meters deep. Some scientists have proposed that Venus may have had stable liquid water on its surface for as long as 2 to 3 billion years, possibly supporting conditions that could have been hospitable to life. The young sun was less bright than it is today, which may have meant that Venus received only slightly more solar radiation than Earth does now. With a modest atmosphere and liquid water, Venus might have had surface temperatures not very different from Earth's, oceans, perhaps even rain, possibly even life. But at some point, the sun brightened. The oceans on Venus began to evaporate more rapidly. The water vapor in the atmosphere increased the greenhouse effect. The increased warming caused more evaporation. The runaway greenhouse effect took hold. The oceans boiled away. The water vapor was broken down by ultraviolet radiation high in the atmosphere, with the hydrogen escaping into space and the oxygen reacting with surface minerals. The temperature climbed. The carbon dioxide from volcanic outgassing accumulated in the atmosphere because there were no longer oceans to dissolve it and no longer life to process it. And Venus became what it is today. This scenario, if correct, means that Venus and Earth began their lives as very similar planets and followed very different paths due to a relatively small difference in initial conditions. Venus is slightly closer to the Sun. It receives about 1.9 times as much solar radiation as Earth. This relatively small difference in energy input, amplified over billions of years through the feedback loops of the greenhouse effect, may be what separates a world with oceans and life from a world with sulfuric acid clouds and 465-degree surface temperatures. In 2020, a team of scientists announced the detection of phosphine in Venus's atmosphere. Phosphine is a gas composed of one phosphorus atom and 3 hydrogen atoms. On Earth, phosphine is produced primarily by biological processes or by industrial chemistry. Its detection in Venus's atmosphere at levels that could not be explained by known non-biological chemistry caused enormous excitement in the scientific community because it raised the possibility that something in Venus's atmosphere might be producing it biologically. The upper cloud layers of Venus, while extremely hostile by most measures, have temperatures and pressures that are actually somewhat similar to conditions on Earth. Some scientists have speculated that microbial life could potentially survive in the cloud droplets at these altitudes, using chemical energy from the surrounding atmosphere. The phosphine detection remained controversial. Subsequent analyses by different scientific teams reached different conclusions about whether the phosphine signal was real or an artifact of the data analysis. The question is not yet settled, but the possibility that life, if it ever existed on Venus, might have survived in its cloud layers as the surface became uninhabitable is now a legitimate scientific hypothesis rather than pure speculation. Magellan's mission ended in October 1994. After completing its radar mapping campaign and several extended mission phases that collected gravity data and performed atmospheric experiments, it was commanded to enter a special orbit that caused it to encounter Venus's upper atmosphere and use the atmospheric drag to study the upper atmosphere directly. On October 12, 1994, Magellan plunged into the Venusian atmosphere and was destroyed. Its last transmission was received as it began its terminal descent. It had spent 4 years at Venus, mapping 98% of the surface and revolutionizing our understanding of this planet. The legacy of Magellan is the map, a nearly complete, high-resolution portrait of a planet that cannot be seen with optical instruments from space. Every volcanic feature, every corona, every mountain range, every tessera terrain, every rift valley was revealed by the patient radar mapping of this spacecraft. Scientists have been studying Magellan's dataset for 30 years and are still making discoveries in it, including the volcanic vent change discovered in 2023 in archival data collected more than 30 years earlier. The dataset is a gift that keeps giving. Several new missions to Venus are now in development. NASA has approved 2 missions that are expected to launch in the late 2020s or early 2030s. Da Vinci, which stands for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging, will send an atmospheric probe into Venus's atmosphere, descending through the cloud layers and measuring their chemistry in detail, while also imaging the surface in infrared wavelengths. Veritas, which stands for Venus Emissivity, Radioscience, INSAR, Topography, and Spectroscopy, will orbit Venus and produce a new radar map of the surface with resolution about 100 times better than Magellan's, along with measurements of surface composition. The European Space Agency is also developing a Venus orbiter called Envision, which will complement the NASA missions with its own set of instruments. Together, these missions will transform our understanding of Venus in the same way that Magellan transformed our understanding in the 1990s. They will map the surface in unprecedented detail. They will measure the composition of the atmosphere at every altitude through the cloud layers. They will look for signs of ongoing volcanic activity. They will search for evidence of past oceans, and perhaps they will settle the question of whether something lives in Venus's clouds. Let us spend a moment thinking about what it would actually be like to descend through Venus's atmosphere. Not in a thought experiment about survival, but as a purely observational experience, imagining what each layer would reveal. From high above Venus, looking down from orbit, the planet presents as a featureless sphere of dazzling white. No surface detail, no variation, just the tops of the clouds, reflecting sunlight with extraordinary efficiency. The cloud tops catch the light and throw it back with a brilliance that makes Venus glow. This is the face Venus shows the universe, a mask of cloud. Descending into the cloud tops, you enter a different world. The white becomes translucent, then layered. You are surrounded by the upper cloud deck, droplets of sulfuric acid suspended in the atmosphere at about 70 kilometers altitude. The light here is still relatively bright. Sunlight filters through the upper layers, diffused and scattered, but still present. The temperature here is actually fairly mild by planetary standards, around minus 40 degrees Celsius, not far from temperatures found in the upper troposphere on Earth. The pressure here is about the same as Earth's surface pressure. If you could breathe the atmosphere, which is impossible given its composition, the physical conditions of pressure and temperature would not be immediately lethal. But you cannot breathe it. The atmosphere here is mostly carbon dioxide with sulfuric acid droplets and sulfur dioxide gas. The droplets would corrode metal over time. They would destroy unprotected biological tissue. The absence of oxygen would be fatal to any Earth organism within minutes. Descending further through the middle cloud layers at 50 to 60 kilometers altitude, the droplets become larger, the light dims, the temperature rises to around 0 degrees Celsius, the pressure increases, the cloud deck becomes denser and more opaque, the sulfuric acid chemistry becomes more complex, with larger particles of unknown composition adding to the droplet mixture. Below the main cloud layers, from about 45 kilometers downward, the atmosphere begins to clear. The cloud droplets thin and disappear. The sky is not clear in the way Earth's sky is clear on a cloudless day. There is still haze, still a murky orange-tinted translucence that scatters and absorbs light, but the dense cloud ceiling is above you now, and you can see further. The surface, perhaps 45 kilometers below, remains invisible in the haze. But the atmosphere around you takes on its characteristic deep orange color, the color of the light that is filtered through 70 kilometers of cloud layers above. As you descend through the lower atmosphere, the temperature and pressure rise steadily. At 30 kilometers, the temperature has climbed to over 200 degrees Celsius, and the pressure is several times Earth's surface pressure. At 20 kilometers, it is over 300 degrees Celsius. At 10 kilometers, approaching 400 degrees Celsius, and at the surface, reaching 465 degrees Celsius and 92 times Earth's surface pressure. The light at the surface is dim but not dark. Scientists estimate that the surface illumination is roughly equivalent to a heavily overcast day on Earth. Perhaps like being outdoors under a thick blanket of storm clouds and twilight, enough light to see by, enough to make out the landscape around you, but filtered through so many kilometers of cloud and haze that the sun itself is not visible, just a general brightening in the direction of the sky where the sun would be. And what would you see at the surface? The Venera images give us our best guide. Flat, dark rocks, angular and fresh looking, some with a layered structure suggesting volcanic origin. Soil between them, reddish brown, made of weathered rock particles and volcanic deposits. The horizon would be closer than you might expect, because the dense atmosphere refracts light in unusual ways, bending the light along the surface so that the landscape appears to curve upward slightly at the edges. The effect would be disorienting. The surface would appear to curve inward around you rather than away from you. The chemistry at the surface is extraordinary. The high temperature and the composition of the atmosphere drive chemical reactions between the atmosphere and the surface rocks that do not occur on any other planet. Carbon dioxide reacts with certain minerals. Sulfur dioxide reacts with others. The rocks at the surface are in chemical equilibrium with the atmosphere, a dynamic equilibrium that depends on both temperature and pressure. If you collected a rock from Venus's surface and brought it to Earth, it would begin chemically reacting with Earth's cooler, lower pressure atmosphere and eventually transform into something different over years or decades. Venus's rocks are specifically adapted, in a chemical sense, to the specific conditions of Venus's atmosphere. Impact craters on Venus are relatively few and have an unusual distribution. Venus has far fewer craters than other inner solar system bodies like Mars, Mercury, or the Moon. This tells us that the surface is geologically young. Impact craters accumulate over time, and a surface with few craters must be recently formed. The relative youth of Venus's surface is consistent with the hypothesis that global volcanic resurfacing events have repeatedly buried older terrain under fresh lava. The craters that do exist on Venus have distinctive characteristics. Many of them show evidence of volcanic modification, with lava flows that have partially flooded the crater floors or swamped the crater walls. Some craters have irregular shapes or are associated with unusual dark splotches that may represent the impact site where the incoming meteoroid broke up in the dense atmosphere and exploded before reaching the surface, leaving a splatter pattern rather than a clean, circular crater. Venus's thick atmosphere acts as a shield against smaller impactors, which are decelerated and often destroyed before reaching the surface. Only the larger ones, with enough momentum to punch through 90 atmospheres of air pressure, make it to the surface intact. This means Venus has almost no small craters, only medium and large ones, a size distribution that is quite different from other rocky bodies in the solar system. The distribution of craters across Venus is also interesting. They appear to be distributed randomly across the surface, with no obvious concentration in particular regions, and no areas that appear significantly more cratered than others. This is consistent with the global resurfacing hypothesis. If Venus periodically resurfaces itself through massive volcanic eruptions, all regions would be about the same age after such an event, and craters would then accumulate uniformly across the entire surface until the next resurfacing event. Magellan's gravity measurements, collected during its extended mission phases, revealed important information about the interior of Venus. Unlike Earth, where the topography is strongly correlated with the underlying crustal structure in ways driven by plate tectonics, Venus's topography appears to be supported more directly by dynamic upwellings in the mantle below the crust. The highest topography on Venus corresponds to regions where mantle plumes are pushing upward on the crust from below. When a plume weakens or disappears, the topography above it should subside. This dynamic support mechanism is fundamentally different from how mountains are supported on Earth, where they are held up by the isostatic balance of thick, buoyant crustal roots. The interior of Venus is thought to be broadly similar in structure to Earth's interior, with a metallic iron core, a silicate mantle, and a rocky crust. But the details of the core structure are unknown. In particular, scientists do not know whether Venus has a liquid outer core like Earth does. Earth's liquid outer core, moving under the influence of Earth's rotation, drives the dynamo that generates our magnetic field. Venus has essentially no global magnetic field, which might suggest it has no liquid outer core, or that its core is not convecting in the right way to generate a magnetic field. But Venus's very slow rotation might also explain the absence of a magnetic field, even if it has a liquid outer core, because the dynamo mechanism requires both a conducting liquid and a sufficient rotation rate to drive convection in the right pattern. Understanding Venus's interior, particularly its core, is one of the major goals of the upcoming Veritas mission. The comparison between Earth and Venus is one of the most important exercises in planetary science, because it is fundamentally a study of contingency, of how small differences in initial conditions can lead to wildly different outcomes over billions of years. Venus and Earth formed from the same disk of material around the same sun, at similar distances, at roughly the same time. They have similar sizes, similar masses, similar compositions, and yet one of them developed oceans and a moderate climate and billions of years of biological evolution. The other developed an atmosphere of carbon dioxide 90 times as thick as Earth's, clouds of sulfuric acid, and surface temperatures that melt lead. The difference that drove these divergent histories may have been small at first: a slightly different initial inventory of water, a slightly different orbital distance that led to slightly more solar radiation, a slightly different geological history that led to more or less volcanic outgassing of carbon dioxide at critical moments. Whatever the initial difference was, it was amplified over billions of years by feedback loops that pushed Venus toward its extreme state and kept Earth in a habitable range. Understanding this divergence is not merely of academic interest. It is directly relevant to our understanding of habitability across the galaxy. As we discover planets around other stars, we are finding that many of them orbit in the zone where liquid water could exist on their surfaces. But being in the habitable zone does not guarantee habitability. Venus is in the habitable zone of our solar system, or very close to its inner edge, and Venus is not habitable. Understanding why Venus is the way it is, and how it got that way, helps us understand which exoplanets in the habitable zones of their stars might truly be habitable, and which might be Venus's. This is one of the most important scientific questions of our era. Are Earths common or rare? Are Venuses more common? If planets similar to Venus in size and composition but slightly closer to their stars, routinely undergo runaway greenhouse transitions and become infernally hot, then the universe may have far fewer truly habitable worlds than optimistic estimates suggest. If, on the other hand, Venus was pushed into its current state by unusual circumstances, and most Venus-like planets in similar orbits remained habitable, then the universe may be full of worlds with liquid water and the potential for life. We will not know the answer until we understand Venus itself much better. And that understanding is coming, slowly but surely, mission by mission, dataset by dataset, discovery by discovery. You are very close to sleep now. Let everything settle gently. Let the orange world of Venus drift peacefully in the background of your mind, the thick clouds turning in their rapid 4-day circulation, the surface below, hidden and hot and volcanic, shaped by forces that have been at work for billions of years, the mountains of Maxwell Montes with their metallic frost, the coronae scattered across the volcanic plains like rings pressed into clay, the lava flows spreading across the surface in the dark, with no one to watch, on a world that has been alone in its extremity for longer than complex life has existed on Earth. Venus is our nearest planetary neighbor. It orbits just inside our own orbit, and at its closest approach it comes within about 38 million kilometers of Earth. It is closer to Earth than Mars ever gets, and yet it is perhaps the least understood of all the inner planets, because its clouds hide its surface so effectively that we were essentially blind to its geology until Magellan arrived. Now we know, and what we know is extraordinary. A world that may have been habitable, a world that underwent a catastrophic transformation, a world of volcanoes and acid clouds, and crushing pressure and searing heat, a world that despite all of this is still geologically alive, still erupting, still changing, still keeping some of its secrets for the missions that are coming. Let the story rest now. Let Venus keep its secrets for tonight. Let the orange glow of its clouds fade gently into the dark behind your eyes, and let everything be quiet and warm and still. You are home. You are safe. The atmosphere of Venus presses down on its own surface, far away and beyond imagining. And you breathe the thin, sweet air of Earth, warm and comfortable, and exactly right. Sleep now, sleep well. Good night.